Let's keep on talking about inverse trig functions here. So we talked about the sine and the cosine and the inverses for those. And now we want to deal with the other 4 trig functions, right? So we have 6 trig functions in total. We have sine, cosine, and tangent. Then we have secant, cosecant, cotangent. Remember that when we talked about sine and cosine, one of the things that we said is, of course, sine and cosine, you can't actually get true inverses for those functions. The problem is that they're not one-to-one. Because they're periodic, they're really badly not one-to-one. But what we did was we said, okay, we can do this by thinking about them on a restricted domain. So, for example, when we did sine, we said, if I think of sine x on an interval from minus pi over 2 to positive pi over 2, it is one-to-one on this interval. So we defined the arc sine inverse of x equals y, means that the sine of y is equal to x, and also it means that y is in the interval from minus pi over 2 to positive pi over 2. And then we did something similar for cosine. So go back and watch the other video if you forget about that, or just consult your book. So we want to do the same kind of thing for tangent, cotangent, secant, and cosecant. So the first ones that I want to deal with actually are going to be secant and cosecant. Let's do secant and cosecant first. So remember that secant of theta is the reciprocal of cosine theta. Remember that the co gets flipped here. So secant goes with cosine, cosecant goes with sine. And so what we want to do here, remember that cosine inverse has the following definition. So cosine inverse theta, or I should say cosine inverse of x equals theta. This means that the cosine of theta is equal to x, and also theta has to be in the interval from 0 up to pi. So if I want to talk about the reciprocals here, then I can do that for secant pretty easily. I can say, well, let's go ahead and let's think about just how would you get the inverse here for this kind of thing. So in other words, what I want to do is I want to say that secant inverse of theta being equal to x, this means that secant of theta is equal to x, and, oh, I'm sorry, give me one moment. Okay, sorry, I just had a student send me a message, and I wanted to make sure that it wasn't anything super important in the middle of this. So, returning to this problem at hand, we want to say also that theta should be in the interval from 0 up to pi. But here's the thing. This is going to need to exclude theta being equal to pi over 2, because for pi over 2, secant is undefined. So actually, the range is going to be 0 up to pi over 2, unioned with pi over 2 to pi, and it'll include 0 and pi, but it will not include pi over 2. Now, something that I want to notice here is that if the secant of theta is equal to x, then there's something we can say about the cosine. So if secant theta is equal to x, then the cosine of theta is 1 over x. Because remember, secant and cosine, these are reciprocals of each other. So these two things are equivalent. That means another way of thinking about this is that to say that secant inverse theta equals x means the cosine of theta is equal to 1 over x. And this gives us a kind of an interesting thing that we can do here. Because this means cosine inverse of theta so let me put it this way. So this means that if I want to say, I wanted to say secant inverse of x equals theta means cosine, that's what confused me here. I wrote an x in place of a theta and a theta in place of x. Starting over for a moment here. If the secant inverse of x is equal to theta, this means that the cosine of theta is 1 over x. That is correct. I now have all of my thetas and all of my x's where they belong. And what this means is that the cosine inverse of 1 over x is equal to theta. So there's actually a nice little bit of a relationship here between secant inverse and cosine inverse, which is exactly what we would expect here to find, since secant and cosine are reciprocals of one another. We can do the same kind of thing here, okay, when we're talking about cosecant and sine. So I wrote down sine theta a minute ago at the beginning and sine inverse theta. Now we want to see, what does that tell us about cosecant? Well, we're going to do the same kind of thing for cosecant. So cosecant inverse of x equals theta. This means that the cosecant of theta should be equal to x. And remember that this is the reciprocal of sine. So we want this to land in the angle between minus pi over 2 and positive pi over 2, because that's the range for inverse sine. So we also want theta to be in minus pi over 2 up to positive pi over 2. And this is going to exclude 0, because at 0, sine of 0 is 0, and so cosecant of 0 is undefined. Since cosecant is the reciprocal of sine, it can't be defined at that point. So another way of thinking about this is that theta has to be in minus pi over 2 up to 0, unioned with 0 up to positive pi over 2. So we don't include 0 as an option here. Now, notice that another way of thinking of cosecant theta being equal to x is that this means that the sine of theta is equal to 1 over x. Okay, so in other words, there's this nice relationship here where we can kind of think about, what would all of these things be? Now, how can you use that fact to help you out? Well, one of the ways that you could potentially use this in order to help you out is, let's say, suppose we want to find the cosecant inverse of negative square root 2. Well, we could potentially try to find this by looking at tables and things like that. But what we can say is that this, if I call this theta, this means that the sine of theta is equal to negative 1 over the square root of 2. Now, negative 1 over the square root of 2 is actually negative square root 2 over 2. And what is an angle between minus pi over 2 and positive pi over 2 whose sine is negative square root 2 over 2? Give you a second here to think about that. I want to see if you guys can come up with what would that angle be. Well, the answer is that angle would be theta is equal to minus pi over 4. So how did this help me? The way it helped me is I kind of know something about sines and cosines. Those are kind of the easy ones to work with. And the reason that they're easy to work with is because those are just the x and the y coordinates of the terminal point. We don't have to do anything with them. See, cosecant is actually the reciprocal of the y-coordinate, and that's kind of a more complicated thing. So if I can turn my questions into a question about sine and cosine, that is always to my advantage to do. Well, I won't say always. I mean, there's always going to be exceptions, right? But as a general rule, if you can say, here's a trigonometry question, and we can rephrase it in terms of sines and cosines, that often will help you when you're thinking about it. Okay, so we took care of secant and cosecant, finding the inverses for those. Now, what about tangent and cotangent? Well, these are going to be just a hair trickier. Tangent and cotangent, let's do tangent first. Remember that tangent theta is actually sine theta divided by cosine theta. So what we're going to do, sorry, I'm pacing like I tend to do when I talk and walking out of the camera here. So what we're going to do is we want to ensure that we have a domain on which this thing is 1-to-1. This is 1-to-1 if we restrict ourselves to minus pi over 2 to positive pi over 2. And this time notice that I want to use the open parentheses. I don't want to include these end angles. The reason for that is at these endpoints, the denominator here would be 0, and so this whole thing would be completely undefined. Okay, so I can't include the endpoints here. So we will define the inverse tangent of x to be equal to theta. This means that the tangent of theta is equal to x, and theta is in the interval from minus pi over 2 to positive pi over 2. Let's talk a minute about the domain and the range of this function. The domain is actually all reals. Why? Because tangent actually goes from minus infinity to positive infinity on this interval. Go back to where we graphed tangent a while back. It's probably easier to just look in your book than to try to find the video, but we did do this in one of the videos as well. But if you look at this thing, from minus pi over 2 to positive pi over 2, this thing actually looks like this. This is like the world's fastest sketch, okay? Obviously, I didn't even label anything, but it really does go all the way from minus infinity to positive infinity. Another way of seeing that is to notice that, well, just think about what this ratio does. For angles near negative pi over 2, this ratio is negative and the denominator is tiny, so we go all the way down to negative infinity. And we come up through 0 because at an angle of 0, the numerator is 0. And then, as we get close to pi over 2, sine and cosine are both positive this time, and the denominator is tiny again. So we're blowing up to positive infinity. The range of this function is going to be minus pi over 2 to positive pi over 2. So this is my definition of the inverse tangent. You can also write this as atan x or arctan x. So remember we talked about how some people call these the arc functions, so arc sine and arc cosine instead of cos inverse and sine inverse. Same deal with tangent, cotangent, secant, and cosecant. Some people call them arctangent and write them this way, you know, an arcsecant, cosecant, and so on. Last one we need to deal with is inverse cotangent. So for cotangent inverse, cotangent of theta is going to be 1-to-1 on the interval from 0 up to pi. So we define inverse cotangent of x equals theta, this means that the cotangent of theta is equal to x, and theta is in the interval from 0 to pi. So it's very similar to the tangent definition, or the inverse tangent definition, except notice that we have shifted the range here for theta. So again, the domain for this is going to be all real numbers, but the range is going to only be 0 to pi. Now, how do you remember the range for cotangent versus the range for tangent? Well, the key is this. Remember that cotangent is cosine over sine. We can't allow the denominator to be 0. So we cannot include any place that has a y-coordinate of 0. The y-coordinate is going to be 0 on our unit circle, at 0, and at pi. So I can't include those two. I either have to pick the upper half circle or the lower half circle, and we pick the upper half. For tangent, on the other hand, we have sine over cosine. Well, cosine would be 0 at minus pi over 2 and positive pi over 2, and we take the right half of the circle, where the denominator is never 0. Okay, so that's kind of how you want to remember these ranges for the inverse tangent and cotangent here. Now, just like we did last time with sine and cosine, there are some subtle things that you have to worry about. For example, suppose that I wanted to do inverse tangent of, let's say, 5 pi over 4. I can't just say, oh, this is going to be 5 pi over 4, because remember, this is not a true inverse. If it were a true inverse, then that would work. But it's kind of a cheating inverse. It's really only an inverse if we restrict the domain here. So what we need to do is we need to change this angle to an angle with the same value for the tangent, but it needs to be between minus pi over 2 and positive pi over 2. So this is going to equal theta, where tangent theta is equal to the tangent of 5 pi over 4, and theta is in minus pi over 2 to positive pi over 2. Okay, so how can we do that? Well, here's the thing to remember. Tangent of theta plus pi times k is the same as tangent of theta. So I just need to add or subtract multiples of pi until I get something which is in this interval here. Now I notice 5 pi over 4 is too large. So I try subtracting pi. 5 pi over 4 minus pi, this is equal to pi over 4. That is in the correct interval here. It's between minus pi over 2 and positive pi over 2. And tangent of pi over 4 is equal to tangent of 5 pi over 4. So this is the angle that I want as my answer here for what is the tangent inverse or arctangent of the tangent of 5 pi over 4. Let's work out a different example using cotangent here to illustrate kind of the same idea, but how it works with cotangent. So let's suppose that I wanted to do cotangent inverse of cotangent of minus pi over 7. Okay, so once again, the thing that I want to remember is that this is some angle theta where the cotangent of theta is equal to the cotangent of minus pi over 7, And theta is in the interval 0 up to pi. Okay, this angle, the minus pi over 7, doesn't meet both of these conditions. It works for the first one, does not work for the second one. It is not in the correct interval. But what we can remember is, once again, cotangent of theta plus pi times k is the same as the cotangent of theta. In other words, I can add or subtract multiples of pi, and I don't change the value of the cotangent. Because I don't change the value of the cotangent here, that means I can just take this original angle and I can start adding or subtracting multiples of pi to it until I end up with an angle that is between 0 and pi. So if I take minus pi over 7, I might notice that's too small. I want to get that bigger to get it to land in this interval. If I add pi, then that is going to become 6 pi over 7. And that is in the correct interval. So this is the answer that I want. One more thing that I want to illustrate here is that